Hi everyone, we are back and we are going to talk about the central limit theorem and then effectively start to determine a methodology for calculating real approximations to the population mean for both large and small sample sizes. So right now we've been calculating confidence intervals, which is great, but we assume that we know what the population is, which is never possible. And plus, again, we are trying to somehow get an estimate from a sample mean to see how close it is to the population mean, or to get basically an estimate where mu is approximately going to be equal to this, plus or minus, some confidence interval. So we haven't been able to do that yet. So let's go ahead and start with an example of how we've been doing things so far, and how we can kind of start to approach this problem. So let's go back to my research. So I performed a bunch of experiments looking at the rolling velocity of particles. I have 138 particles. We predicted that, again, it should exhibit a mean of 3 micrometers per second, standard deviation of this. And again, we can kind of approach this how we've been doing it so far. So actually, let's pull up R. So, and let's try to go over here. And here, we'll get this over here. And we'll start to, let's zoom this out a little bit. Let's develop this kind of experimental package. So we don't need to install tidyverse because we already have it. So we can do library of tidyverse. We do need to, I think we do have ggplot. We do need install packages of write Excel. So that's going to take a little bit. Now we can read in there. So we can create essentially this data set. So I'm going to create the roll data based on what we have discussed here. We're going to put it in a plot, and then we're going to write this as basically here. And we'll do it to users, and then let's see if it works here. So boom, boom, boom. So let's go ahead and try to find it. And we can read that in as well. Actually, we can go and look it in here. So let's go to home. I wonder if we can go to, let's actually build this out a little bit. Let's go ahead and take a peek. Can we go further into computer? Let's go, well, actually, I tell you what, let's go to, instead of lab view data, let's go, actually, can we go desktop? No. So instead of this, I'm going to put this into a folder, which is going to be my documents, and I'm just going to put it in the documents here. So I'm going to go ahead and set this as my directory. So set as working directory here. So you can kind of see I can build in this function right here. So after I've created this, so set my working directory, and then I want to open, actually I'm going to do read underscore exe, let's do read dot xl, let's see if we can do, we need to actually build in a function read Excel. Read dot underscore Excel. So here we go. So we need to actually install the package. And again, this is just kind of getting install dot packages. We need to install packages of, and actually to write Excel, we need this. Can't have that. So install packages. We need to do, read Excel, and then we need to do library, and then we'll see read Excel. There you go. So now we should be able to do read. So I'm going to set my, again, this is bad, this is bad verbiage, but I'm going to do read underscore Excel, and then we're going to go to, basically, if we go to here, their files, we're going to just type in rolling velocity dot xlsx. We should be able to roll it in. We could look at that roll dat now, and you can see essentially the numbers. Yay! All right. So we can go ahead and actually we'll call this, and we'll call the roll dat. Actually, we'll call this rolling velocity, and then we'll pull that out and we'll look at roll dat here. So we can look at the roll data. So it's just going to pull out that first. So roll dat here is just going to be those numbers. So we can take the mean, you get the value, you can take standard deviation, and we can go ahead and calculate those confidence intervals and some of those values as we've kind of seen previously. But anyways, we're getting a little bit ahead of ourselves. We can also look at a distribution as well. So looks pretty Gaussian, which is nice. So we can actually, and we can even plot a Gaussian on top of it, which is very cool. But anyways, we're getting a little bit ahead of ourselves here. And let's go back to our notes. So if we wanted to calculate and prove that in a 95% confidence interval, the Walker velocity won't move more than, will not deviate more than 0.5 micrometers per second, we can look at the data set. It looks Gaussian. We can try to apply our previous methodology, which is calculate our mean, calculate our standard deviation, which we did there. And we know that our 95% confidence interval will just be 1.96 times that standard deviation. And we can plug that in, and you can see this is value. So even in the 95%, we're going to deviate, or our average velocity will deviate a bit more from this. Ignore this number. This is from a previous data set, and we're going to keep kind of updating this with our new methodology, so just be aware of that. Can we disregard 1.6 as an illegitimate data point or an outlier? Well, let's actually go into that. So we have, this is our mean, and we actually saw this up here. So we could look at the mean here. So if we do mean, and then I'm going to pipe the mean minus standard deviation. So remember, it needs to be, what was our metric? 3. So if it's less than, so, oops, actually, let's go ahead. Instead of piping that, I can just do this. So if it's less than 1.6, or if it is greater than this, then that is an outlier. So I think the problem was, again, it's kind of ridiculous at this point, but anyways, you'll visualize that. So 1.6 is definitely, actually it is an outlier. So there you go. Now, again, we've just been doing what we've been doing previously, but now we have to get into our central limit theorem. And central limit theorem is critical because, again, we found the dispersion of values around essentially a mean value. We've done a 95% confidence interval, but we have not estimated the uncertainty in our sample mean to the true population mean. So if we were to do this, you'd have to kind of repeat this example over and over and over and over again. And it's kind of an impossible idea. But we are going to invoke one of the most profound and powerful theories in our central limit theorem. So we've been working and to do that distribution, to calculate those confidence intervals for a data set, we have to assume that we are Gaussian. And that's not necessarily, we don't know, again, that's, even if the sample's Gaussian, who knows what the population is? And we've seen lots of different types of populations. And for example, let's look at the uniform population. We can't use our analysis for this to calculate that 95% confidence interval. But instead, even if a population looks like this, we can invoke the central limit theorem. And it's a very, very interesting idea, which is as long as you obtain a large value of means, so n is greater than 30. So if we have lots of mean measurements, you can actually see, central limit theorem says that if you look at the distribution of the means, so this is a distribution of the means. So in this measurand here, it's x bar. So if you look at the distribution of means from any distribution, if you increase the sample size large enough, it will look Gaussian. And this is incredibly powerful. So let's look, and actually let's look for, and actually here you can see, we're going to do an exponential, Poisson, uniform, and then let's look at our, and this is our uniform data plot here, and we're going to run a little for loop. So I'm going to sample basically 5 data points, and we're going to calculate the mean of each of those 5s. So I'm going to sample, and you can kind of see this here. So I'm going to run 5 means, and I'm going to sample at least 30 data points. So I'm going to sample 30, calculate a mean, and repeat that 5 times. So we can kind of see that here in the list. So I'm going to do that. Oh, sorry, we need to do here. Here, here, and then we're going to look at. So already in 5, it's looking pretty good. But let's go ahead and instead, let's do like 10. Again, let's adapt our bin width. So instead of a bin width of 5, you can just say a bin width of 1. It's probably too much. Yeah, it's a little bit. So this one's again, it's not giving us a perfect Gaussian. Let's increase it to 30. Now we're getting somewhere. Now it's starting to look a little bit better. What if we increase it to 50 for an exponential, for example? That looks pretty Gaussian to me. So you could also increase it here for the uniform. So let's say, for example, we did 50. So we can go bang, bang, bang. That looks pretty Gaussian as well. So that was for an exponential. What about a Poisson? Let's sample, sample, sample. Looks pretty Gaussian to me. So this is incredibly powerful. What it tells us is something extremely profound. We don't care about the underlying distribution of the population, because we could always, if we measure means and we get a large enough sample of means, that distribution of the means will always be Gaussian. So we can follow the exact same formalism that we've developed previously. So, but we do have to make some changes. So now we're going to switch, instead of looking at the standard deviation of the we're going to look at the standard deviation of the mean values. So we're going to take the standard deviation of our population divided by, or excuse me, if I'm looking at the standard deviation of the means, I need to look at the standard deviation of our measurements and divide by the square root of n. And we can do the same thing here, where we're going to replace that in our z expression, and we will eventually get to where we can rewrite this as this expression here. This is our confidence or uncertainty level in the population mean, based on what we measure, which we can measure, essentially the means of our means, and then standard deviation of our means. So basically this would be like your, x bar effectively, but again, that's equal here, over square root of n. So this is our key data point, our key measurement. The z over 2 is just your confidence interval. So again, if it was 95%, it's still going to be that 1.96 value. But the big difference in what we did previously versus what we did now is you see that we have this factor of 1 over square root of n. So you can always, if you increase the number of measurements, you will shrink essentially that uncertainty. And it's the same thing that we've been seeing with sampling and all these other things moving forward. So central limit theorem is extremely powerful, extremely, it's a profound theorem actually. And it enables us to use a lot of cool statistical analysis and tools. And it's very broad in general, which is always great for any theory. So we'll see you all next video when we talk about beer. I know it's very odd, but it's relevant. Trust me. See you next time. Bye.